Friends, how are you? I hope you all are well. A new day, a new beginning. Today's topic is transfer of heat, or you can say conduction of heat. The transfer of heat may takes place in three different ways. One is conduction, convection. Third one is the radiation. Out of these three processes, usually conduction carried in solid, whereas the convection carried in liquid as well as gas, and radiation does not require any medium. In this video, I am going to explain conduction. So, what do you mean by conduction? Suppose this is a metallic rod. One end of the rod I am showing to the candle flame. What happens? The end of the rod which is in contact, which is near the flame, it receives the heat energy. As a result, the molecule, those are present here, they get heat energy, their kinetic energy increases. As a result, they start to vibrate with a higher speed. Their temperature increases. The reason is that their kinetic energy increases. Then what happens? They collide with the nearby molecules. As a result, there will be a sharing of a kinetic energy from molecules of higher energy to the molecules of lower energy. At the same time, these molecules also start to vibrate. Like this way, the heat transfer from one end of the rod to the other end. Here, the average position of the molecules are not changing. The average position of the molecules will not change. Molecules will not move from one end to other end. Just they will vibrate about their mean position. Due to their vibration, their kinetic energy increases, or you can say the temperature increases. They collide with others. This collision continues from one end to other end. That means the transfer of heat carried out from one end to other end through the molecules only. Here molecules does not move permanently from one end to other end. Their average position remains same. So I can say that there is no transfer of mass. There is no transfer of mass. Only there will be a transfer of heat. The heading I have written heat transfer. So now we discuss about the conductivity. See here, suppose I have taken a metal rod of uniform cross section. It's uniform cross section. Suppose this area of cross section is A and this length is X and let its temperature is T1. The temperature of this end is T2. There is a difference in temperature. In this case, T1 greater than T2. Remember, heat transfer only possible if there is a temperature difference. How much temperature one place does not matter. For example, here 500 degrees Celsius, here 500 degrees Celsius, there will be no net transfer of heat energy. So, heat energy transfer depends upon the difference in temperature. For example, this is 500 degrees Celsius, this is 100 degrees Celsius. There will be flow of heat from left to right. So, heat transfer does not depend how much temperature there or how much it depends upon the temperature difference. How much difference will be more, that much fast will be the transformation of heat. So, I can say that the flow of heat depends upon temperature difference. So, there should be difference in temperature between these 2 points. As a result, there will be a transfer of heat energy. So, our topic is heat transfer, or I am discussing now conduction. Conduction means the process of transfer of heat, that is the conduction. And every substance having its ability, the ability of transfer of heat is measured by thermal conductivity. The ability of conduction of heat is measured by thermal conductivity. So, what is that thermal conductivity? Listen. Here, how much amount of heat is flowing? See here. Suppose this is a cross section. This is a cross section. You think that after sufficient time, a steady state is reached. In which state the temperature difference at any point equal. What? See, this is the area of cross section, this is the area of cross section. How much heat is flowing through this point? Same amount of heat is flowing through this point. I am telling. I want to say that when after sufficient time a steady state is reached where same amount of heat flow per second through any cross section. I have taken a metal rod of uniform cross section in this case. How much heat is flowing here? Same amount of heat is flowing. For example, 1 joule of heat is flowing here. Here also 1 joule. You cannot say that here 1 joule, here 0.5 joule. It is not possible. Suppose here it is passing 1 joule of heat energy, here 0.5 joule. After some time, the amount of heat gathered in this area will increase, which is practically impossible. So, I said that after sufficient time, a state is reached where we find the temperature at any point will be equal. So, I am telling that point. So, the area of cross section is uniform. Steady state is reached. In that case, you can find that the heat flowing per unit time, the amount of heat flowing per second. Suppose delta Q is the heat, the temperature is difference is the temperature is the delta T. So this is the rate of heat. This rate of heat is directly proportional to change in temperature. This delta Q upon delta T directly proportional to change in temperature. How much heat will flow per unit time depends upon the difference in temperature, not the temperature. Difference in temperature between the 2 points from where to where it will travel. So I can say that delta Q upon delta T directly proportional to T1 minus T2. At the same time, this delta Q upon delta T, this is the rate of a flow of heat. We say heat current. This is the rate of flow of heat, not heat. Rate of flow of heat, amount of heat flowing per unit time, directly proportional to change in temperature. It is directly proportional to area of cross section. So this is one equation, this is second equation. Directly proportional to difference in temperature, directly proportional to area of a cross section, this area of a cross section. So if I combine that, I can get that delta Q upon delta T, delta Q for the heat, delta T for the temperature. I am using capital T. So I can say that this is proportional to A T1 minus T2. One more term is there also. I can say that this rate of heat also directly proportional to, this rate of heat is inversely proportional to its length. That means the length will be more, transfer of heat will be less. So it is inversely proportional to length. This is the third equation. So if I combine these three, I can find that this delta Q upon delta T is directly proportional to A into T1 minus T2 upon X, or you can write delta Q upon delta T equal to K into A into T1 minus T2 upon X. So this is the fourth equation. So what is this K? This K is called thermal conductivity. Here K is called thermal conductivity. K is thermal conductivity. K is called thermal conductivity. So what is the SI unit of a thermal conductivity? See here, this delta Q upon delta T is the rate of a flow of heat, or I mentioned here is the heat current. So I can say that this K is equal to delta Q upon delta T into X upon A into T1 minus T2. Then what will be its SI unit? Its SI unit will be, this is the current, heat current. So I can write this is joule per second. This X represents the distance, length of the metal rod what I have taken. So I can write this is meter, area of cross section meter square, change in temperature I can use this is the Kelvin, or I can say that this is joule per second per meter per Kelvin, or you can say this is watt per meter per Kelvin, or we can write watt per meter per degree Celsius, because the difference of temperature of 1 Kelvin and 1 degree Celsius both are equal. So this is the unit of thermal conductivity. So thermal conductivity, I said that this is the ability of conduction of a material measured by thermal conductivity. Now let us see. Suppose the substance is not uniform. The substance what I took earlier example, I took it uniform. Now for example, this is not uniform, and or the steady state is not reached. Steady state reached in the sense at every cross section the rate of flow of heat I found, or I found that temperature difference same. Suppose this substance is not uniform, or it is not reached in the steady state. At steady state I used to say that the rate of flow of heat is directly proportional to area of cross section, directly proportional to change in temperature. Now for example, you consider very less thickness. Very less thickness. Suppose this thickness is dx. This thickness is dx. Very less thickness. And the temperature is dt. So in this case, I can say that this delta Q upon delta T is equal to minus K A into dx upon dt. Here K is the thermal conductivity, A is the area of cross section. Here dx by dt is the temperature gradient. Here dx by dt is the dt upon dx is the temperature gradient. Minus sign indicates the temperature gradient is against the direction of a flow of heat. So one thing I want to say that in this all these examples, the surface of the rod what I am using, it is protected from outside. That means it is insulated. From the beginning what I have been telling, only this side not insulated, but the remaining portion, outer portion is completely insulated. That means there is no chance for the heat to escape through this way. Here also same thing, this is also protected. So in this case I said that the negative sign indicates this, the dt upon dx is against the direction of a flow of heat. This is called the temperature gradient. Temperature gradient means, see here, suppose this is a conductor, this is one more conductor, the lengths are different. I am taking these two cross sections. Here also I am taking two cross sections. Both thickness here and here equal, but the temperature difference not equal. Suppose the temperature difference here is 10 degrees Celsius. Here the temperature difference is 8 degrees Celsius. Listen carefully. This thickness same. This area of cross section same. Instead of that, its length is more. Here the temperature difference is less. Here temperature difference is more. When the temperature of difference will be more, there will be more flow of heat energy. When the temperature difference will be less, there will be less flow of heat energy. So this difference in temperature, this is called the temperature gradient. That means if the temperature gradient is more, there will be more flow of heat energy. When temperature difference or the temperature gradient is less, there will be less flow of heat energy. So here dx represents the thickness, whereas the dt represents the temperature. So this is about the temperature gradient. So now let us move to one example. So before going to example, I can say that solids are better conductors of heat than liquids. Liquids are better than gases. And so far solids concerned, metals are good conductors of heat than non-metals. That's why our cooking vessels are made out of the metals. Many cases you might have find the bottom portion of the vessel of the cooking vessels are made out of the copper, because it is a good conductor of heat energy. There is a good transfer of heat energy. So transfer of heat energy required in every stage of our life. For example, in case of the nuclear reactors, there should be transfer of heat energy, because during the nuclear reactions, huge amount of heat energy produced. To maintain the reactor core within a certain limit, how much it can tolerate, there should be a transfer of heat energy. So the transfer of heat energy through metals comes under the conduction, because here heat transfer due to vibration of the molecules, not due to shifting of the molecules from one place to another place. Let us see an example. So K is the thermal conductivity, dt upon dx, I said temperature gradient. For example, the temperature of one end of a copper cube, the temperature of one end of a copper cube of is 10 centimeter is 100 degree, and other end 0 degree Celsius. Calculate the amount of heat to K into A into difference in temperature upon length of the conductor. So, in case of copper, its thermal conductivity is 385 joule per second per meter per Kelvin. So, I can use this is 385 into area cross section. Here I have mentioned the temperature of one end of a copper wire of edge 10 centimeter. That means 0.1 meter. 0.1 meter I can write. So, into change in temperature. So, this is 100 minus 0 upon length. Okay. Here length is taken 10 centimeter or 0.1. So, this is area cross section. So, I can use 0.1 meter square. Okay. Unit last I shall use it. So, 0.1 square written area cross section. The value of this thermal conductivity K equal to 385 given and change in temperature. The one side is the higher temperature 100, lower temperature is 0. So 100 minus 0 upon 0.1. So I can say that this is 385 into 0.01 into 100 upon 0.1. So this will be equal to 385 into, so this is 1 upon, so 0.01, 1 upon 100 into, this is 100 to 10, so 100 cancel. This is equal to 385 joule. So this is the amount of heat per unit time. So I can say this is 3850 watt. So I hope that this class you might have understood very well. So children, if you want to study continuously, consistently, you have to subscribe the channel. At the same time, you have to press the like or dislike button along with subscription. I hope that you understood this lesson. Thank you.